Okay, are we ready? What we have here is a container, right, that has some gas particles in it. It kind of looks like it's a liquid, but we're going to assume that it's a gas, okay? This top here, that lid is not movable, okay? So for this time, right, let's just write that the lid cannot move. When we study the other gas laws, that lid will be able to move. But for this gas law in particular, right, we're going to maintain that volume, do you see it here? That volume is constant. But we're going to change the temperature. And we're going to model what happens when we change the temperature. There's going to be two scenarios. The first scenario is when we cool it down. The second scenario will be when we heat it up. So the first thing that I'm going to do in these two boxes is I'm going to redraw this. Now I want it to be just a little bigger than what it has here. So mine's going to look just slightly different. But what you should know, right, is that the container stays the same. So we're just drawing, right, our versions of this container. Remember, this lid is going to stay kind of right in the middle. Okay? And then this is the pressure gauge. So up here in our example, or our room temperature, our medium temperature, it's at 2. I just put a 2 there. I'm going to put a 1 and a 0, and then a 3 and a 4. This measures the pressure inside our container. Okay? Then I'm just going to draw another one on this side. Same thing. At least as close as I can get. Oh, I totally smeared that one. Okay, with drawings? Good. Remember, right, if volume is constant, what we're saying is this, right, top lid stays in place. The space is the same. Right, for both scenarios. We do also have to make a few notes down here at the bottom. This remember section, okay? We're going to write the amount of gas inside the container stays the same. We are not adding more gas, right, or taking particles away. Okay? The number of particles, we're going to call that variable n. is constant. And then the last little note that we have to put here is you must convert temperatures to Kelvin in calculations. Okay. Remember I said you can't have negative numbers when we're doing these gas law calculations. The only scale that doesn't have negative numbers is the Kelvin scale, our absolute temperature scale. Okay. Everyone got this? So if the number of gas particles is constant, do you know how many gas particles I need to draw in each of my models? It has to be the same, and the same as up here. So I can count 1, 2, 3, 4, 5, 6, 7, 8, 9. So I would draw 9 circles, right, in each of my containers. They should all be about the same size, right? Okay, they don't have to be in the same position. I obviously didn't make them in the same position. Doesn't really matter. Okay, but you should have the same number of particles. That shows me, right, that the number of particles is the same. The amount of gas in there is the same. When we cool down, right, the temperature, what's happening to the motion of the particles? Yes, they slow down. Or, in scientific terms, we would say that it decreases, right? Remember, we're showing motion or speed of the particles using arrows, right? So is the arrow going to be big or small? Long or short? Shorties, right? So what I'm going to do is I'm going to make these little guys super short. And you can point them in whatever direction you want. It's totally up to you. But you should make them super short because they are not moving fast, right? Short arrows, not moving fast. If they are not moving very fast, what happens to the number of collisions? Yes, there are less collisions. Again, less means decreases, right? Less means decreases. On this other hand, right, if I am heating this up, what length should my arrows be? Super long, right? And if they're close, what happens, right, if they were to come into contact with the container? They start to bounce and cause collisions, right? Remember, temperature is a measure of the motion, how fast these particles are going. And so when we draw longer arrows, what we're drawing is that these particles are actually moving, right, a farther distance. And remember, when we are drawing our particles and our arrows, right, if they bounce off right? If they bounce off, what we need to do is make sure, right, that we put X's at all the points that they are bouncing off. What do the X's mean again? Good, these are collisions, right? So more X's means what? More collisions. More collisions means what? More pressure, absolutely. So the motion has speeds up. We'll call that increases, right? Our scientific vocabulary. And so our collisions are more, or they also increase. And you can see that in our pictures, right? This side has no collisions because they're moving really small arrows. This guy has lots of collisions, really lots of arrows, bouncing long arrows. I do want to just also, right, I have a pressure valve here. Is this going to be more or less than the 2 that's up here? This pressure, am I going to measure it to be higher or lower? I'm going to measure it to be lower, absolutely, right? Less collisions, lower. More collisions means higher pressure, so I'm going to point it, right, higher, maybe between 3 and 4. Good. Now let's go through these bold statements here. We are changing temperature, so as temperature increases, what is happening to pressure? Right? It also increases. When one variable goes up and the other variable goes up, right, they are directly related. This gas law that we're learning is named after a French scientist, and his last name was Gay-Lussac. So this is Gay-Lussac's law. It's kind of a funny word, funny last name, right? Yeah. But it's a guy's last name. It's not like I made up the name of the law. The graph, right? I'm going to do it in black. Here are my X and Y, right? And my independent variable is temperature. My dependent variable is pressure. And what's my line going to look like? If they're directly related, one is increasing and the other increases, I'm just going to draw a straight diagonal line. Okay. Then the equation is actually really easy. P1 over T1 is equal to P2 over T2. Okay. You'll always use this equation to solve when pressure and temperature change and volume, right, is constant and the number of particles is constant. Remember down here we wrote you must convert temperatures to Kelvin. Okay? Because this has temperature in the equation, you always have to make sure, right, that you convert to Kelvin.